you get the hang of it, it's easier.
So it's not.
I'm telling matrices at first, but then the big idea is to solve 3x3 systems using matrices. Okay, so in the last chapter we looked at solving 3x3 matrices just by manipulating equations. Here we're going to look at using matrices to do that. So first, just a little bit of vocab. A matrix is just a rectangular array of numbers. Okay, usually we use it to organize a set of numbers. Okay, and the biggest thing we're going to use it for in this first section is organizing equations. So we've got a few different types of matrices. Right? A square matrix is just where we have the same number of rows and columns. So that could be a 2x2 or a 3x3 or a 4x4 or a 5x5 matrix. A row matrix just means we have something like this, right, where we've got one row, but a bunch of columns. A column matrix, also kind of self-explanatory. We have one column and a bunch of rows. And then another vocab word, the main diagonal. So, main diagonal, I'll just write out a 3x3. So the main diagonal is the diagonal set of entries that goes from the top left to the bottom right. Main diagonal goes from the top left to the bottom right. And as we start looking at ways to solve these systems using matrices, the main diagonal is going to be a key here. Okay? So the first thing, just a basic idea with matrices, is the order, okay? Describing how a matrix shows up. We always describe a matrix as the number of rows by the number of columns. Okay, it's always the number of rows by the number of columns. So in this first one, okay, we have 2 rows and 2 columns. Okay, so we would say that this is a 2x2 matrix. Okay. So how about the second one? How many rows does this have? 1. How many columns? 2. So it's a 1x2. Okay, the only thing that you could mess up with this is looking at the number of rows and columns backwards. Right? So rows are side to side, columns are up and down. So for the third one, we have 3 rows, 2 columns, so 3x2. Say 2x2? 2x1. Yeah, we have 2 rows and 1. Okay. So that's how we would describe each of these matrices. Okay. Questions so far? So now, at the bottom here, setting up a matrix to describe a system of equations. So what we're going to do is take all of the coefficients and write them in what's called an augmented matrix. There we go. So if I want to solve this system of equations, I want to make sure that all my x's are in a row, all the y's are in a row, or I'm sorry, a column, all the z's in a column, and all my constants on the right side of the equation. So then I just take all of the coefficients and write them in an augmented matrix like this, where I put all of the coefficients of the variables here in a 3x3 matrix, and then we just draw a line. And this line kind of acts as the equal sign, and put all of our constants on the right side of that line. So the first column is just the coefficients of x. The second column, the coefficients of y. Third column, the coefficients of z. The final column contains the constants. So to solve a matrix like this, we're essentially going to be doing the same thing that we did in the last chapter. We're just going to organize it differently. Okay? And hopefully this organization will allow us to do these problems quicker. So these are the operations that we can do. Okay? I can interchange two rows. I can multiply a row by some constant. And I can add a multiple of one row to another row. Okay? Just like we did with the equations. Right? We multiplied equations by constants and added them together to try to cancel out variables. So this is very similar to what we did in the last chapter. All right, so vocab term. A matrix is in row echelon form. Okay, row echelon form. If it has these three properties. The leading entry of each non-zero row is 1. Okay? The leading entry in any row is to the right of the leading entry in the row above it, and all non-zero rows are above the rows consisting entirely of zeros. So what that looks like, okay, our goal is to make our matrix look like this, okay, where the leading entry is 1, and then the next entries can be whatever. But then I want the leading entry of the row below it to be to the right of the leading entry in the row above it. Okay, that's what number 2 means here. The leading entry in any row is to the right of the leading entry in the row above it. Okay, so this is the goal, to make our matrix look like this. Okay, I want my main diagonal to have all 1s. It doesn't matter what these numbers end up being. Okay, these can be whatever. That's why I wrote them as A, B, and C. But then we want zeros down here. Sunk your battleship. Wait, isn't the destroyer the one with 3 pegs? The battleship has 4. Alright? Sure. Alright. I mean, I know this seems a little weird so far, right? But hopefully it'll make more sense when we do an example here. But any questions so far? Alright, so let's take a look at an example here. Well, I put these in there just in case we didn't finish notes. You'd rather watch it than watch me? That's fine.
I don't understand the multiplying videos. We'll see what the videos are. And then we can comment.
Sure. No, that's mad.
Oh, well, let's watch the ads.
Row, our coefficients are positive 1, negative 1.
Alright, I'll restart it here.
Our second row, we have 0, Okay, here I'm going to use Gaussian elimination to solve a system of equations. We've got x plus y minus z equals 9, y plus 3z equals 3, negative x minus 2z equals 2. So the first thing I'm going to do is write down my augmented matrix. So from the first row, our coefficients are positive 1, negative 1. Our constant is 9. Our second row, we have 0x, we have 1y, we have 3z. Our constant is 3. From our last row, we have negative 1x, we have 0y, negative 2z, and our constant is positive 2. So what we're going to do is, our goal in this case is we want to write this in row echelon form. So the idea is we're going to write the matrix so that it's in triangular form and where the leading coefficient in each row is equal to 1. Okay, so to do this, I look at my first row. I want the first non-zero entry in the first row to be a 1. So in this case, we've got a positive 1 here. Again, the idea is if you kind of look along the diagonal, forget about the constants. If you look along the diagonal x, y, z, we're going to make the entries below that into zeros. We're going to make the constants all equal to 1. That's what we're shooting for here. Okay. Once we do that, we're going to use some back substitution. So again, my goal eventually is to get zeros here, and I want 1s along the diagonal. That's what we're going for. So that'll kind of be step 1 here. Okay, so to get a 0 in the third row, first column, I'm just going to take row 1 and add that to row 3. That's going to replace my row 3.
So we are going to use
I like to use
this
a little arrow
notation. Okay, we're going to write these operations
That's
down.
arithmetic, these problems. So anything I can do to help keep myself organized, I always found that helped. So I'm not changing the first row, not changing the second row either. And now I'm going to do my arithmetic. So 1 plus negative 1 will be 0. That's what we wanted. 1 plus 0 will be 1. Negative 1 plus negative 2 will be negative 3. And then 9 plus 2 will be positive 11. Okay, so again, we want 1s along the diagonal. Again, forgetting about the column with the constants. Well, we do have a 1 in our second row, second column, so that's good. We said we wanted to get zeros everywhere below that diagonal. Okay, everywhere below that diagonal. So I need to change the entry in the third row, second column. I want to make that into a 0 as well. Well, if we just add row 2 and row 3, that's not going to do the trick. But if we multiply the second row by negative 1, then add that to our third row, I think that'll do it for us. So let's see here. Again, I'm not changing the first row at all. I'm not changing the second row either. Now I'm going to change the third row again by doing the arithmetic. So negative 1 times 0 plus 0, that's just 0. Negative 1 times 1 will be negative 1. We add negative 1 to positive 1, we'll get 0, which is exactly what we wanted. Negative 1 times 3 is negative 3. Negative 3 plus negative 3 will give us negative 6. Negative 1 times 3 again will be, well, negative 3. Negative 3 plus 11 will be positive 8. And now we've got our third row. Alright, here, getting close. The last thing again we want to do is we want to make our first non-zero entry in the third row, which is our negative 6. We want to make that into a positive 1. Well, what I'm going to do to the third row is simply, and we divide by negative 6. We don't really think about division so much. We always talk about multiplying by non-zero constants. So I'm going to multiply the third row by negative 1/6. That's going to give me my new third row. So in essence, you're just dividing the third row by negative 6. Again, not doing anything. The first row, not doing anything to the second row. Negative 6 divided by negative 6 would be positive 1. 8 divided by negative 6, well, that would be 8 over negative 6. We can reduce 8 over 6 into 4/3, again, not getting negative. Okay, so now we've got our matrix in the form that we want. And what we do now is we go back and write the corresponding set of linear equations, and then we start using substitution, back substitution to solve. So recall this is the column corresponding to x, the column corresponding to y, the column corresponding to z, and then our constants. So we've really got these system of equations: 1x plus 1y minus 1z equals 9. From our second row, we've got 0x plus 1y plus 3z equals 3. From our last row, we simply have that positive 1z equals negative 4/3. Okay, so now we know what z equals. The idea is we can take that and substitute that into the second equation, solve for y. Then we'll have both y and z. Then we can substitute that into the first equation and solve for x. Okay, so using our second equation, we have y plus 3 times z. That's negative 4/3. That equals positive 3. Well, the 3's would simply cancel out, so we would have y minus 4 equals 3. And if we add 4 to both sides, we'll get that y equals positive 7. Okay, so now I'm going to take these two values and simply put those back into our first equation. So give me an x plus y equals 7 minus the value of z, which is negative 4/3. And that's going to equal positive 9. Alright, so very close here. We've got x plus 7. We have plus 4/3 equals 9. And you can always get common denominators and add and subtract fractions. I'm going to get rid of the fractions, or I should say fraction, by multiplying both sides by positive 3. So we'll have to distribute that. We'll get 3x. 3 multiplied by 7 is positive 21. 3 multiplied by 4/3 is positive 4. 9 times 3 will be 27. So we have 3x plus 21 plus 4 will be 25. And if we subtract 25 from both sides, we'll get 3x equals 2. And if we divide both sides by 3, we'll get that x equals 2/3. So now we've got our solution. It says the solution to the system of equations would be when x equals 2/3, we said that y equals 7, and z equals negative 4/3.
I don't think I've ever learned something so
So 10 minutes.
not only did you make no, really. He only spent 8 minutes and 54 seconds.
That's how
I feel like we could have solved that in like
I understand.
4 minutes flat.
Hey, dude,
The y is convenient.
we're going to practice doing it this way for now.
So if you give us homework, you told us to do this, by that, you'll do the answers. But it wasn't this, we could do that out of time.
Yes.
Are there any cases where you have to do this, like the other method won't work?
I think that's
That's so, you're so full of crap.
You totally think so. All right, so let's take a look at the second example here. Okay, I want to put this first into a matrix.
It's a 5-minute problem.
Like I said, once we get the hang of this, it'll go a little bit quicker.
Yeah, we'll go a little bit quicker.
So if I turn this into a matrix, it'll look like this. Two. Okay, so my goal is to get these values to be 0 and my main diagonal to all be 1s. Well, I don't think that's going to work either. So, it's good thinking. So remember, our 3 options, we can switch rows around. We could multiply the first row by 1/2. Okay, we could do that. Or we could switch the first and the third rows to just make that 1.
Just switch it.
We can switch rows.
This one's down here now.
Yes.
I feel like this is just like.
Okay, so there's multiple things that we could do here. I mean, I probably am not going to multiply the first one by 1/2 because then I'll get a bunch of fractions. I don't really want to deal with fractions.
Right when you said this line, you just kind of draw.
So I'm just going to switch the first and the second rows here. Or I'm sorry, the first and the third rows, not first and second.
Do we have to do the R?
Yes. Okay, I want you to explain the operation that you're doing. Okay, so if I do that, I'll have 1, 1, -1, 6, -3, -4, 2, 4, 2, 1, 1. Oops, this should be a -2. There we go. Okay, so now I want to start adding things together, or adding multiples of rows together to get zeros here. Right? So again, there's multiple ways that we can do this. Okay, but I'll say if I multiply the first row by 3 and add it to the second row, I'll get a 0 there. Or we could add the first and the third row together. We could multiply this by -2 and add this to get a 0 here. Either of those would work. We can do what Alex said first. We can take the first row, or let's see, what did we say? -2 times the first row plus the third row, and we're going to put that in place of the third row. Okay, so I'm not changing the first or the second row. Those are going to stay the same. So 1, 1, -1, -2, -3, -4, 2, 4. But now I'm going to take -2 times the first one and add it to the second one. So that'll be -2 plus 2 is 0.
Yeah, I'm just thinking for a second, the rest of this
Video to watch. So -2 times this plus this. So -2 plus 1 would be -1. And then -2 times -1 would be +2. Plus 1 would be 3. -2 times -2 is 4. Plus 6 is 10. So now we could get rid of this one. So we could say I'm going to do -3 times the first row plus the second row and put that in place of the second row. So the first row is going to stay the same. 1, 1, -1, -2. Now -3 times 1. Wait a minute. Oops, that should just be a +3, shouldn't it? Sorry. +3 times the first row. So 3 times 1 minus 3 is 0. 3 times 1 plus -4. So 3 plus -4 would be -1.
Wait, do that again. I'm serious.
So
No, just the -1.
So 3 times 1 is 3, plus -4,
Oh, okay, now.
-1. So then 3 times -1 is -3, plus 2, so -3 plus 2 would also be -1. 3 times -2 is -6, plus 4, -2. And then we're not changing the third row, right? So 0, -1, 3, and 10. Now, the only thing I still have to eliminate is this one. Okay? I need to turn this one into a 0. How can I do that?
Add first, third. No.
Well, if I had the first and the third, this one would no longer be 0.
You gotta multiply the second by.
Yeah, so let's add -1 times the second row plus the third row, and we'll put that in place of the third row. So I'm not changing my first or my second. So 1, -1, -2, 0, -1, -1, -2, and now, so -1 times 0 plus 0 is still 0. -1 times -1 would be 1, plus -1 is 0. -1 times -1 is 1, plus 3 is 4. And then -1 times -2 is 2, plus 10 is 12. Okay, so now my goal is to get my main diagonal to all be positive 1s. Now, we can probably do a couple of these operations in one step, right? I want to multiply the second one by -1 to make this a positive 1. And then multiply the third one by 1/4 to make this a positive 1. Okay, so we can do both of those operations at once. We can say, I'm going to do -1 times R2, and that'll go in place of the second row. And then also 1/4 times the third row to go in place of the third row. So that'll become 1, 1, -1, -2, 0, 1, 1, 2, and then 0, 0, 1, 3.
I'm gonna have everyone to do the substitution now.
So now, what we have is x plus y minus z equals -2, y plus z equals 2, and z equals 3. So we know z equals 3. I can plug this back in up here. Say y plus 3 equals 2. Subtract the 3 over. Y equals -1. Then I can take the 3 for z and the -1 for y and plug them in up here. So x plus -1 minus 3 equals -2. So -1 minus 3 would be -4. Add 4 over. We get x equals 2. So the answer is 0.2, -1, 3. Once we get the hang of it, like I said. Okay. Questions?
Yes.
No.
How do you just like come up with
Please excuse the interruption. Just an announcement about this morning's musical preview. Students, at the end of second period, please proceed to the Performing Arts Center so that you can see a small snippet of the musical. We will do that during third period. Staff, if you don't mind, please help escort students into the auditorium and get them seated, and then spread yourself out amongst the auditorium area.
Questions?
How do you manage to come up with like -1 or 2? Everything else makes sense. But you just do that.
Because that's what you're multiplying.
This one right here? Or you just mean in general?
Just in general, how do you look at it? Like, oh, I should multiply by 6.
So, I mean, right here. My first goal was to get a 0 right here. So, I need to add these two numbers, like the 1 and the 2 together somehow to get 0. So if I multiply this one by -2, I'll have -2 plus 2 equals 0. So it's just like we were doing before, where we have to figure out how to cancel out the x's. Here we just have numbers instead of with the variable, just have the coefficients. So we're just looking to see, well, if I add this one with this one, how can I cancel those out to get a 0?
That's why it takes like 8.
Yeah, because our goal is to get zeros here, here, and here. Okay. Other questions? It's usually easiest to get the zeros first. Yeah. And now, I mean, if we had some equation where like everything was divisible by 2, then we could definitely just multiply by 1/2 to reduce it like that. But in this case, like if I multiplied this one by 1/2 first to make this one a 1, I would get fractions, and that would get messy. Other questions? We got 7 minutes. Oh, come on. Southcon.
I think he's behind. You run Khan Academy?
I love Khan Academy. All right, there is one more form of a matrix that we can use to solve systems. That is by putting that in reduced row echelon form. Okay, so row echelon form that we just talked about was getting our main diagonal of 1s and then zeros in the bottom below the main diagonal. Reduced row echelon form looks like this. Where I've got zeros everywhere else, and then these values can be whatever, right? So reduced row echelon form is where we not only get 1s in the diagonals and zeros down here, but also zeros up here. Right? So then
just directly gives you
exactly, then it just gives you the answers. We would say x equals a, y equals b, and z equals c. Right? So we don't have time, I don't think, to go through this example. So your homework tonight is going to be to watch the video that goes through this example. And then I will send it to you to remind, yes. Right. So watch this video, try example number 3, or do example number 3 along with the video, and then try example number 4 on your own. Okay, that's your homework.
I don't have a graphic calculator.
You don't need a graphing calculator at all.